Let's first show you once again what we're talking about. If I draw my phase diagram where I have my temperature and my pressure, here's the phase diagram from back in 121, Chemistry 1210. Here I have my two lines. The solid line is my solvent. The dotted line is my solution. Let's say we are running at 1 atmosphere, okay? That's the purpose of this line, 1 atm. That would be the normal boiling point. Again, from Chemistry 1210. So what's going to be the actual boiling point value? When I drop the line down to the x-axis of temperature, this will be my solvent boiling point, the full line. When I drop my line down here, this will be my solution boiling point. And the distance in between, we call that the delta TB. So I've shown you the picture first. Now let's talk about the words. You know from the section before, the vapor pressure of a solution is always lower than the vapor pressure of the pure solvent. This was going to be my dotted line, and this is going to be my solid line, okay? And it's going to follow Raoult's law. Well, we just showed on the picture that the boiling point of a solution is going to always be greater. Again, if I had my blackboards, this would be sitting on the board. I could point to everything at once. We have a very simple equation. Notice delta TB, that's called the boiling point elevation. M, that is the molality. We taught you about it in an earlier section. And KB, that is a constant. It's called the boiling point elevation constant, and it depends on the solvent. People found from experiment that for water, it was 0.52 degrees centigrade per molal. Where did it come from? Well, they took a 1 molal aqueous solution of a non-volatile, non-electrolyte, and they saw that it boiled at 0.52 degrees centigrade. So the delta TB was equal to 0.52 degrees, and that's where they came up with the molal constant. You do not have to memorize it. It is provided. Okay, I have to say that right. Let's show in a problem what we would do. We want to know what is the solution boiling point. Well, whatever it is, we're going to have to add on our delta TB. What information haven't they given us? 35 grams of our solute. It has a molecular weight of 164 grams per mole. They told us 450 grams of water, that is our solvent, and they told us the KB, 0.52 degrees centigrade per molal, and they told us the boiling point of water, 100.00 degrees centigrade. So if you were with me last semester, I always said try to work everything out in one line so you can tap it into your calculator. Delta TB, that's what we're looking for. We want to know what's the change. KB, 0.52 degrees centigrade for every molal. Now what I'm going to do is I'm going to do my entire molal calculation in one spot. I'm going to say 35 grams and 1 mole weighs 164 grams. That's going to be my moles on top, and on the bottom I'm going to say 0.450 kilograms of water. Yeah, I know people usually don't work like this, but I think it works a little bit better for our level of course. What we come out with is a number 0.25 degrees centigrade. That is our boiling point elevation. So if this is the boiling point of water and we have a solution, we're going to be adding on 0.5 degrees centigrade. Our boiling point will be 0.2 degrees centigrade will be the boiling point of solution. Yes, it is new, but I don't think it's all that hard. Just think about what you're doing, practice it until it flows. That's our boiling point elevation. Now we also have what's called a freezing point depression. And what I did is I'm just using one slide to describe the whole thing. If this is my phase diagram, and if I focus in where is the solution vapor pressure for the melting point, freezing point? You notice that the line is to the left, and if I once again draw in 1 atmosphere, which is the normal melting point, I can see I will have 2 different numbers. I will have one line that drops down. This is my solvent. And I will have a second line that drops down. This is my solution. And the distance in between is the delta TF, the change in freezing point, okay? So the freezing point is always lower than that of a pure solvent. And here is the equation that we use. TF, freezing point lowering, M is the molality, and Kf is the molal freezing point depression constant. So we're going to do another problem. We're going to use the numbers in a little bit different way, but again, it's very, very versatile. They can ask it in more than one way. So let's write down our facts. We have 15.0 grams of ethyl alcohol, and that is turning out to be our solute. We have 750 grams of formic acid, which, since it is the larger number, it is our solvent. And it says to us the freezing point of the solution was 7.20 degrees centigrade. It gives us the freezing point of formic acid to be 8.40 degrees centigrade. Here, they're saying evaluate the Kf. Normally they ask for what is the freezing point, what is the change. Here it's a little bit different. So what we want to do is we want to calculate that value. I'm just going to rearrange the equation because I think that's the easiest way to do it. We are solving for Kf, and it will be the delta TF divided by the molality. So let's see, what do we have? Well, the delta TF, 8.40 minus 7.20 degrees centigrade. And what is our molality? Well, I think I did this one on the side. I said I have 15 grams of ethyl alcohol, and I know 1 mole weighs 46 grams, and my value of kilograms of formic acid, 0.750 kilograms of formic acid. So again, this part is the solute, and this part is the solvent, and I come up with a value of 0.435 molal. Yeah, I normally put it in, but I said I'm just going to break it into pieces. So essentially, 0.435 molal. When I crunch my numbers through, I come up with 2.76 degrees centigrade per molal. Remember, a lot of chemistry 1220 is algebra. It's not, you could just give these numbers to someone, give them the formula, and honestly, you should be able to come up with the numerical answer. The important part is understanding what is underlying it, and that's why I tried to draw the pictures to show you how this is really working. Well, there's one more property here, and before I go there, there is a table of all of these constants sitting in your textbook or in your e-text. It provides you the normal boiling point, the normal freezing point. It gives you the constants. So we give you these things, but generally solutions do not behave very ideally. They tend to vary, and you know about that from intermolecular forces from chapter 11. So these constants, they are very good if I have a dilute solution. Wrapping up this section will be osmotic pressure. There's a lot in there. So I ask you, before you go on to read part 3, please read through this slide. See if it can make sense to you so that when I start talking about it, we can be on the same page.